Okay, I hope my presentation slides are visible.
Yes, yes. You can go for full screen. Presentation mode. Can you click on present?
Yeah, just yeah, I hope it's visible. No? Okay, so I'm.
No, I can't see it. So if you look at the bottom, right, there is a option for presentation, or you can press F5. Yeah, that one. Yes. Yeah.
Okay.
Yeah, you can start now. Yes.
Okay, so we are presenting the paper Cyclone detecting contention-based cache information leak through cyclic interference. So this is the overview. So first, just some background. So in the class, we already learned some of these hardware attacks, and along with that, we will look at a property called cyclic interference, which is the key principle which is used in this paper. And then we will look at some isolation methods, like how different applications running on same hardware are isolated. So first, the hardware attacks. So we have seen contention-based attacks using both side and covert channels, like flush preload and prime probe. And then we saw speculation-based attacks like Spectre and Meltdown. And then what is cyclic interference? So suppose you have this scenario, you have spy and victim. And now this is prime probe attack scenario. So first the spy tries to access the cache, which is denoted here. The spy primes the cache, that is he fills the entire cache with his data. And then in the next phase, then the victim tries to access the same cache. So when the victim tries to access the cache, the spy's data is already there, so he has to evict the victim. So that means now there is some contention created for the victim because of the spy. So that is shown using this curving arrow at the top. And then in the next phase, when the spy again tries to access the same cache, now the cache is filled with the victim's data. Now the spy has to evict the victim's data. That means now the spy is facing some contention because of the victim. Now that is shown by this arrow. Now if we see here, now there are two contentions here, one in this direction and one in the reverse direction. So when we have a contention in both the directions like this, now this is called one interference cycle. So this is cyclic interference. So similar thing we can observe in even the flush reload attack also. So next, moving on to isolation methods. So first is coarse grain. So in coarse grain, so different security domains are separated by different address spaces, like they are completely different processes or they're running on different virtual machines. And the next one, so this is coarse grain is achieved through the hardware memory management unit. The next one is fine grain. In fine grain, multiple security domains share the same virtual address space. Example, if you take a browser, so different websites through the browser, they have the same virtual address space, but the browser isolates the different websites from accessing each other's data. So this is achieved through type and dynamic bound checks. Like it places some checks like beyond this address, you are not allowed to access data. So this is called sandboxing. And yeah, for the paper, this is the main attack model, which this is the scenario which they are considering. So this fine grain scenario is attacks done on this fine grain model is what they want to detect. So next, moving on to the requirements of defense mechanisms. So they propose like there should be whatever defense mechanism that is proposed, it should satisfy at least 5 criteria. So the first criteria, it should support fine-grained isolation. Second, it should be scalable, and then it should handle speculation-driven attacks. And fourth, it should prevent both contention attacks. And if you are going for a detection-based mechanism instead of prevention, then it should have low false positive rate. And finally, it should have a low performance overhead. and then some potential defenses which are already there. So first one is partitioning and flushing,
KP,
and then yes, sir.
what exactly is the goal of this paper?
The goal of this paper is to detect. So the goal of this paper is to detect attacks which are performed in fine-grained isolation setting using this property which I showed before, using this cyclic
Cyclic
interference.
interference, yeah, that I got it.
Uh,
So eventually you will propose a detection mechanism.
yeah, using this, they will eventually propose a detection mechanism which will try to detect these contention-based attacks and also the speculation-based attacks in
Okay,
fine-grained setting.
okay, okay.
And yeah, so some defense mechanisms which are already there, so they are just doing a survey like how many conditions are they satisfying. So these are the three kinds of defense mechanisms. So first one, partitioning and flushing. So in partition, we partition the cache either in space or time, and then we can actually partition the virtual address space. And then flushing is whenever there is a domain change, you flush the entire microarchitectural state like the cache. And what are the limitations of this method? So it has significant overhead. For example, they have performed an experiment with spec 2017 and found out that with way partitioning there is 33% overhead. And similarly, in isolation in Chrome browser there is 10 to 13% overhead. But this defends against both contention and speculation. So but it is not scalable. So in summary, it is satisfying like two of the requirements that defense mechanism should have. The next one is randomization.
Hang on.
Yes,
Why
sir.
it is not scalable?
The scalable is if, for example, if we see here, for example, if you're partitioning the cache like way partitioning, so we have finite number of ways in the cache, right? But as we keep on increasing the security domains or multiple processes, so at certain point we reach the limit. We cannot keep on partitioning the resources. We have finite resources, like limited number of ways.
Okay, okay.
Okay, so this satisfies only two criteria, and then the next one, randomization and encryption. So randomization, we just either try to access the resources like cached in a random way, or do some encryption, decryption. So, but the problem is they cannot defend against the entire capacity attacks, like when the entire cache is flushed. And this, of course, scales well, and it works in fine-grained isolation settings, but it cannot defend against all kinds of attacks. So in summary, this is satisfying three of the minimum criteria required for a defense mechanism. And then the final one, anomaly detection. So anomaly detection, um, so this is like instead of trying to prevent the attack, so we are trying to monitor the system behavior and then look for some abnormal behavior. And this has very low performance. It is easily deployable. So some machine learning model will be trained. So some system parameters, like for example, cache misses will be measured using some performance monitoring unit. This will be given as input to the machine learning model, which will try to identify some abnormal change. So the anomaly detection, it has only one problem. So it has high false positives. So there are different types of anomaly detections. So the first type of detector, generic unsupervised. So we train this on a representative set of benign, that is harmless applications. And the second one, application specific unsupervised. So we train this for a specific harmless application which imitates the behavior of a harmful application. One example is Spectre benign. So if we see here, the left one is Spectre, the right side Spectre benign. So both are behaving exactly same. The key difference is true Spectre will try to reload the array, whereas the Spectre benign, it will do some harmless computation. And then the last one, we just actually make a set of both harmful and harmless applications and train our model on it. So the last one is capable of detecting more different kinds of attacks. So comparison of different kinds of detectors. So here we have a graph called ROC. So here, as we are changing the threshold for different kinds of detectors, how its true positive rate and false positive rate is varying, that is shown here. So for each detector, we have two characteristics. One is with specter benign, that is the harmless application included, that is the dashed line, and without included, that is the solid line. So if we see here, in all the cases, the third detector is performing well, and it is actually advantageous to train it with spectre benign also. And so this is what the preferable one. And but still, in all of this, the false positives are high. So the one of the main goal of this work is to minimize the false positives, and hence they propose the method cyclone. So in cyclone, so the cyclic interference property they will make use of. In addition, they make use of a concept called security lattice, and they use certain tags called domain security tags, and how they propagate. Certain rules are there, and then we'll look at how these things are actually helping in detecting real attacks. And then finally the actual hardware. Then this slide I have just repeated for our recap. Then moving on, what is security lattice? So security lattice is just a specification which specifies like what are all the domains in my system and how data can flow between different domains. So here the data can flow only in a certain way, it cannot go in the other way, and each box is a domain and which is at a different security level. And then the domain security tag propagation rules. So these set of rules define whenever some operation is performed, how either the register or the memory is updated. We will look at one by one. So first, if you look at only arithmetic operation, suppose we have this operation where x1 is the destination, x2 and x3 are the source registers. So if we move ahead, so I will just try to explain with this animation. So let us assume that x1 has a domain tag of kd, so it belongs to this kernel declassified, and x2 suppose has a tag of a, and x3 has a tag of k. Now we are performing this XOR operation. Now according to this rule, the tag of the destination should be updated by this rule. So whichever tag has highest security level, so that tag should be given to the tag of this destination register. So in this case, x2 and x3 are the sources. Among these, x3 has the highest security level. So x1 should be updated to the new tag k. So in the same way, the store also works,
Okay,
and the load
Kirti,
also.
could you slow down a bit? So what exactly is this tag?
Sir, so tag is just identifying which particular process has accessed this last, or which process um, access this last time.
Not clear. So you can go back to the lattice example that you are showing.
Uh-huh.
And yeah, what exactly is the tag here?
So the tag is just identifying which process last accessed it or made some changes on it. And each process has a certain security level, right? Like the process which is at the lowest in this diagram has the lowest security level, and one that is at the highest has the highest security level. Actually, the main goal of this whole thing is eventually they want to use these tags to detect whether cyclic interference is occurring. Like first process A accesses, and then the attacker accesses. Suppose A is some attacker access, then B comes, then C. I think this will be clear when I explain the attacks.
Okay.
Sorry, Vishwa, sorry to interrupt. It's more like if suppose process A has access x2, x2 gets a tag A, and then let us assume that process B has also accessed x2 after process A. Then the x2's tag gets updated to B. And
Okay.
again, when process A accesses the same cache block x2, the tag again changes from B to A. So the tag got changed from A to B and came back to A. So this is a cyclic interference.
That I got it. Cyclic, I got it. So I think
Yeah.
when you are using the term tag, it's nothing but the security domain ID.
Yeah, so security domain ID, sorry to say, yeah, it is getting confused with the cache tag, so it is not actually, but the point is, it is stored along with the tag array of the each cache
Yeah,
block, right?
that's
And
okay.
you
That's okay.
yeah, that's why the tag term is being confusing, but this is how they are trying to detect. I hope now things are clear.
Yeah.
Okay, moving on. So I, I have this load example also, but in the interest of time, I'm just skipping it. I'll come back to it later. So I will just straight away go to the attack. I hope this will make everything clear. So first, let us look at this prime plus probe attack. So here there is a cache block. So there are four parameters, right? So the first one is the resource tag ID, like which domain accessed this resource in the current time. And then what comes after it is which domain accessed this resource in the past time. That is one time step before. And then the last two parameters are like the memory domain tag IDs, like the memory that the address which is being stored here, the data of the address which is being stored here, to which domain does it belong, and same the current tag and the past tag. So if we take prime plus probe attack, so here only the resource tags are helping in identifying the cyclic interference. So that's why they have considered the memory tags as don't care, but even these will get updated according to the propagation rules. So first here, let's assume that A is the attacker and B is the victim. So A has accessed this cache line, and that is why the resource tag for this cache line has become A. Now the victim B accesses the same cache line, and now this A gets updated to B, and then the past tag instead of don't care, now since A is the one who accessed it previously, now this past tag ID becomes A.
Kirti, I
So
think you're confusing cache line with tag. In prime probe attack, attacker and victim, they don't access the same cache line. It's not a shared memory attack. So when you are explaining, you are saying the victim comes and access the same cache line. That is wrong. That statement is wrong.
okay,
It's
it could be
actually
same set, right?
it's same set and same tag bits. The tag bits are the same. That's why you are storing the domain IDs.
Okay.
But cache line is not the same.
Okay. Yeah, sorry. So it should have been same set then.
Same set and same tag. Yes.
Okay. So if we track the history here, so here first from A to B and then again B to A. So here this cycle has formed. So this is one cycle interference cycle. So this is detected. So in the same way, same thing happens in the case of flush reload also. So here one cycle is formed, A to B and again B to A. So here one more interference cycle is getting detected. So interference cycle getting detected doesn't necessarily mean attack is happening, but whenever attack is happening, then obviously there is a cyclic interference. So this is what they are detecting. And then moving on to the architecture, so they are adding some extra hardware to store
I
this
have a
tag.
simple question before we move on
Yes,
to
yes.
the implementation. So
Yes, sir.
even if we have benign applications running on a multi-core system, there is a
Yeah.
possibility of cyclic interference, right?
Yes, yes, there is possibility.
Yeah. So then how will you differentiate?
So what they are doing is they are collecting all such events. How many events are occurring, and if it is crossing certain threshold,
What is
they
an
are
event?
giving. Sir?
What is an event? You haven't explained an event.
So here this event has formed, right? The one which I
The
highlighted.
cycle. The cycle.
One cycle. One cycle is
Okay.
one event.
Mm-hmm.
So they will count how many such cycles have formed in a given time window.
Mm-hmm.
And if this number is above certain threshold, they will give this number and some past history of events as input to some machine learning algorithm, which will based it has been already trained, and it will based on its training it will try to figure out like whether it is harmless cyclic interference, or could it this interference happen because some attacker is trying to do something.
Okay, okay. I have few more questions, but I will ask at the end. Maybe in the interest of time, move on.
Okay. So in the architecture, so they have added extra storage structure, and again at the register level and also at the cache level, these are not the regular cache IDs. These are the tags which are storing the domain security ID. And then LD is the local detector, which is keeping track of how many local interference events are occurring, and GD is the global detector. And this is the structure of the local detector. So this particular structure, it is just trying to detect one event, and here we have an event counter which will keep incrementing as we have number of events. And then we are storing this in some shift register. We are storing the history of how many events occurred in some past n number of cycles. And then if this number of events crosses some threshold, for example here they have taken it as 8, then this signal like valid alert, it will be made high, and this valid alert signal and the entire history of how many events occurred in past n number of cycles, so these will be transferred to the global detector. Global detector can be any one of the three learning algorithms which I have shown in the previous slide, like supervised, unsupervised, for specific, unspecific, etc. So that will try to detect whether there is some attack. And experimental methodology, they have used Champai simulator. And coming to the results, so here they are showing like how many cyclic resource interferences are occurring in the given time interval. So this is a heat map. So here they are actually, this is a false positive stress test. So here whatever benchmarks they have considered, these are harmless spec 2017 benchmarks. So ideally there shouldn't be any dots in this graph, but there are some dots. So wherever dot is there, it is false positive. So since it is very light, that means there are very few false positives. So they have observed that less than 6 events, that is 6 false positive, are occurring for 10 kilocycles. And then this is the information leak test. They have taken an application called benign medical SQL. They have actually taken 4 such applications which are sensitive, which have some sensitive data which should not be leaked. And then here on the left side, they are not performing any attack. So the application is running normally. And here ideally there shouldn't be any pattern, but there are few false positives here and there. And then on the right side, they are intentionally creating a covert channel. So this application is actually leaking some data to another process which is running on the same hardware. So now, if this algorithm works correctly, then it should be detected, and we see that happening here. So here bucket is nothing but it is a counter which is assigned to a group of cache lines. So there we see that there is some pattern here. So it indicates that maybe certain cache set or line we have high number of cyclic interference happening. And then sensitivity across applications. So here they are actually plotting the F1 score. So for any machine learning application, the higher the F1 score, the better the algorithm is performing. So first they have considered a generic classifier, and they are taking some sensitive benchmarks, and they are comparing their method cyclone, which is the last one CRI, against the contention based. It only detects a single interference event, not the cyclic interference event. That is the first bar in each graph, and then the middle one is again the same thing, but they are kind of adding the cyclone hardware to it, but they are not implementing the cyclic interference. And the same thing they are done with a different application specific classifier as well. So here, although it looks like the other algorithms are performing on par with Cyclone, this F1 score doesn't give the full score. So if we actually look at the number of false positives here, so when these are being run on some harmless spec 2017 benchmarks, so we see that the contention detector, that is single interference detector, is generating 300 kilo false positives, and the middle one is 12, whereas the last one, Cyclone, is detecting only 12. And then finally, they are taken a mix of say both harmful and harmless applications and plotting the same F1 score. And here we see the gap between the other methods and the Cyclone is actually pretty high. And then finally, the last graph, they are doing some sensitivity analysis, like varying the hardware parameters, how well the Cyclone algorithm is working. So in first, so one bucket is like one counter. So we cannot assign one counter to each cache line or set. The hardware cost will be very high. So they're assigning some finite number like 4, 8, 16, 32, and they're doing some hash mapping, like based on the cache set index and tag. One cache line will be mapped to one counter. So as they are increasing the number of buckets, the F1 score is very high. But as they are decreasing, then it is the algorithm is not performing so well. But the problem is we cannot keep on increasing the number of buckets. Again, it increases the hardware overhead. And then the second thing, so they are changing the timing interval in which they are observing these cyclic interference events. So the larger the interval, then it performs poorly. But if we keep sampling these events at a smaller interval, then it performs well. And finally, in conclusion, the novel thing in this paper is it makes use of this property called cyclic interference for detection, which is this property, cyclic interference. It occurs in all contention-based leaks, and they are saying it is resilient. It is not completely resilient, but it works very well against. It reduces false positives by a great amount while maintaining decent accuracy. And so this is just a different approach of securing microarchitecture. And the key results, so they have ran the simulation on ARM microarchitecture, and it shows very almost 100% detection rates. And compared to other algorithms, it is achieving 260 to 100,000 times lesser false positives. But one limitation is now, because they have to store these tags everywhere, like at the DRAM level, cache level, and they have to transfer them and modify them, so the DRAM traffic is increasing. So as a result of all of this, there is 2.4% decrease in IPC when compared on spec benchmarks. So that is the end.
Yeah, I have a minor comment. When you conclude, you should conclude your presentation. You should not bring new terms, new numbers in conclusion.
Yes, sir.
With this 260, 1000x, 2.4%, it was nowhere there in your presentation, right? For half an hour.
Okay.
They're all, these are coming for the first time, right? Don't do that. Yeah,
Yes.
so I have a question on the utility. What's the use of this idea? Because you started with isolation, mitigation, then you jumped into detection. So what's the actual conclusion?
So the actual conclusion is, so detection, actually the previous methods for detection, they are using some other performance metrics like cache misses or
No, that's
maybe
okay. That I got it. Let's say I have this cyclic interference based detector.
okay.
Now, what's the use of it?
So use of it, okay. So this is just detecting potential attacks, and this information will be transferred to the higher level, like maybe operating system, and then it has to take the preventive action. It is not preventing actually. So
Okay.
its main purpose is detecting.
And you mentioned about some thresholds, right? To differentiate between benign from non-benign applications. Right?
Yes.
So what if the attacker knows that Cyclone is actually implemented in real processor? and let's say by some form of reverse engineering, the attacker comes to know that okay, this is the threshold, right? Because basically, if you are saying okay, I will allow k number of cyclic interference in 10,000 cycles,
Okay.
and if the attacker knows that,
So I think if the attacker can get what he wants within that threshold, then yeah, maybe this will not work. That
no, no, I'm not talking about whether the attacker will be agile enough to get all the information within this 10,000 cycles. What
okay.
I'm asking is, can an attacker be redesigned to fool Cyclone?
Sir, yeah, Tejeshwar here. So, sir, I would like to add a point here. So, attacker anyways has to take care of timing of attack. So, if we take a look at the basic attacks, prime plus probe or any other attack, attacker has to match the window and match the timings with respect to victim also. So, matching, like adding this another factor will increase the difficulty level of mounting the attack. That's what I think.
Agree. I'm not saying that it's not, but because it's threshold driven, I can always come up with maybe a bit slow attack code, which can still do contention based attack without being detected by Cyclone.
No, see, the difference here is it will still be detected as a
How?
possibility of an attack by Cyclone, because even for benign applications, Cyclone detects it, but it's just that when it is sent to the global detector, right, it has certain performance counters based on which it decides whether this is a benign kind of so because it is a machine learning based trained network, right? So there are certain parameters based on which it decides whether there is an attack or it's from a benign application, and that's how they are trying to reduce the false positives. So I believe it's
Again, I
very rare,
agree.
but it's still possible.
I agree, but
Yeah,
your model is as good as what is available in today's market, right?
absolutely.
So tomorrow, if I come up with a new attack vector that is super slow, okay, I'm not worrying about my agility. It may take a year
Uh,
to attack my last level cache, but
yeah,
it can fool Cyclone.
Yes, sir. So I understand that by so slow, what you're saying is the rate of cyclic interference events will be very less, but he can
Yes.
get the data. Then I think he can fool the cyclone.
Okay. Okay. Yeah. I have so many other questions, but I think I should stop now. Others can ask.
So hi, this is Arnav here. So what is the overhead of this tagging and computation of the event cycles on the normal processing?
What is the overhead? So
Overhead,
yeah,
yeah.
just a minute. So yeah, it is mentioned like for DRAM case, we are having an overhead of 2.4% IPC of, if you are storing tags at the DRAM level. And then at the cache level, there is a slowdown of up to 33% on average and a max slowdown of 40%. This is at the L2 level because you are storing cache at the L2 level. So I'm just giving slowdown because of individual components.
Hey,
And then
why will from where this slowdown is coming from?
so slowdown.
sorry to interrupt, Biswa. The DRAM part, what Kirti said was right, and what you said about the caches was wrong, because essentially they said for the other detectors, right? With them, the kind of partitioning you do, there you have this 33% average slowdown and 40% maximum slowdown.
Yeah.
Yeah,
Yeah,
I'm
with
very sorry.
Cyclone, you should
Yeah,
not get a
sorry.
slowdown. Yeah.
Yeah, no.
Yeah.
Cyclone slowdown is as much as it is reduced to as much as 2.4%
Yeah, that's okay.
for spec benchmarks.
Yeah, that's because your tag store is getting increased with the domain ID.
Yeah,
That's why the
absolutely.
latency will be a bit high, 1 or 2 cycles
Yeah.
here and there.
Yeah, the bandwidth requirement also increases. Yeah.
No, that's okay. That's marginal.
And there are some area overheads also associated with this, because we have to store tags at different cache levels, whether they are private or whether they are shared, and all those things. Yeah.
One quick question. if the attacker uses two processes, one to prime and the other process to probe, will like, then I guess cyclic interferences won't occur, right? That can be a quick fix to not get detected, I think.
Can you repeat the question? I guess I did not understand. If the attacker uses two processes for prime and probe, can you?
So one process is just priming and the other process is probing. Like instead of using just a single process to do priming and probing, which creates the cyclic interference. Because finally it's the PID that's used for the tag thing, right? That you showed.
Yeah, in this case, if the attacker can actually attack using two different processes, then this is useless because you cannot detect cyclic interference.
Okay.
Are you sure?
Yes, sir. Because the main way this is working, the main backbone of this whole thing is cyclic interference, right? And cyclic interference is only tracked through those tags. Only when there is some ABA, that kind of sequence is forming, then it is identifying.
No, the ABA sequence is yet formed right here, but
What?
the difference is there are two different processes.
Yeah. If attacker is using two different processes, then that cycle will never be formed, right?
Okay, so here the cyclic interference, they are tracking using the security tags. So if both the processes of attack are belong to the same security domain, then yes, a cyclone will catch because basically they will have the same tag. So it will still detect it
No.
as a cyclic.
No. This question was two different processes.
I think two different processes will always have different tags.
Oh, okay.
Yeah.
Then it is not possible.
Think about it. Okay. Don't say it's not possible. Think about it.
But particularly, yeah, but that question was really good. We had not thought of it. Yeah.
Okay, maybe one or two more questions before we jump into the next one.
I have a doubt regarding the attack scenario, which was discussed in the previous question. So, it's my doubt is that if you are verifying the cyclic interference at resource level, let's say for cache, so how two different processes can leak information? I do not understand the attack scenario. I mean, the question was whether the cyclone would be able to detect it or not. But my question is that attack scenario itself valid?
Yeah,
For
actually,
program
okay, you are asking like it is related to previous question. Are you asking like can the attacker actually use two different processes to attack?
Yes.
Yeah, even I had this doubt. I'm not sure.
Rishi should answer it.
I thought that an attacker can run, let's say, two processes. I didn't know that this might be
I
very
think
difficult.
it is possible. Just that there should be some kind of synchronization between these two processes. But apart from that, the probing part takes care of the timing. Like it accesses and checks whether it's a cache hit or miss. And for prime part, we are just filling the cache with some random data. So these two things I think can be separated out in two processes.
Yeah, the only thing that you need in terms of protocol is the attacker processes are cooperating processes, right? So they know how to talk to each other.
Yes, there should be some synchronization between these two processes.
Yeah, so simple inter-process communication can still be used, right? Since they are cooperating processes. Even in terms of the security tag, you won't allocate them into two different domains or whatever.
Sir, is this kind of similar to covert channel attack?
No, covert channel is when you are not supposed to communicate, but you are communicating through cache. Here I'm saying, yeah, you have the luxury of inter-process communication.
Okay.
Let's say process 1 wants to say hello to process 3, right? So if that is allowed, then yeah, process 1 can do prime, process 3 can do probe. If there are 100 other steps, micro steps that you want to do, that can be done.
Right.
right?
But then since it has to happen from the same process to detect the cyclic interference, I'm not. Maybe we need to do slight modifications, I believe, in Cyclone.
It's okay. I think you can think about it. Let's not come up with an idea in the lecture itself.
Oh, okay. Yeah, sure, sure. Thanks.
I think Sahil had a question. Is that right?
Yes, hello. Am I audible?
Yeah, go on.
So I was just asking if we are going to use two processes, then it would be even more difficult to ensure that their order remains the same with respect to the victim. So, like
No,
trying
so
to
yeah,
do-
see, it's not that simple. That's taken. It will be really difficult and challenging to mount that attack. But I can still come up with a protocol which can eventually leak information.
Right.
Okay, so good. We had good discussion. So let's move on to the next presenter.
Hello everyone, is my screen visible?
Yes.
So myself Siddharth and I am going to present the paper titled New Attacks and Defense for Encrypted Address Cache. So the main contributions of this paper can be divided into two categories. First is they try to develop fast eviction set finding algorithms that can be used to attack systems which have some cache randomization based mitigation techniques. And then they also try to come up with some modifications to those randomization techniques where these fast eviction set forming algorithms also fail to attack. So this is just a brief overview of conflict-based attacks. Uh, conflict-based attack exploit the ability of the attacker to form eviction set in the LLC, and once they have done that, they orchestrate cache evictions in the victim's process, and by learning their access pattern, they are able to leak some information. So prime and probe is one such kind of attack. So this is just a brief overview. The attacker places lines A and B and victim accesses something, and depending on the misses of A and B, it can the attacker can infer if the victim has accessed a particular set or not. Now we see a randomization based technique to mitigate such conflict based attacks. The key idea here is that the mapping of cache blocks to the memory space is randomized, and this randomization makes it difficult for the attacker to find an eviction set, or even if the attacker finds an eviction set, the mapping changes periodically, and because of which the attacker is not able to attack the victim anymore. So CAESAR stands for cache operated on encrypted address space with remapping. So two key things are there: encrypted address space and remapping. So this is the system overview of CAESAR. Here the physical line address is converted to an encrypted line address using a low latency block cipher, and the cache is accessed using this encrypted line address and also read using this encrypted line address. But beyond the LLC domain, everything else is still physical line address. So all the things that are here, like the prefetch buffers, the coherence request, and all those things will still see the physical line address, and hence we won't require any change. And inside this, we have these two. We have this symmetric key, and this the key here. The key takeaway here is that this key is changing, and because of this changing, the mapping is also changing. So at time t1, we have key 1, and in this example, let's say at time t1, B and D lines are mapped to the same set, and after let's say till the time t2, the key has changed, and because of which the mapping has changed, and now B and D are no longer in the same set, rather C and A are in the same set. So this time between T1 and T2, we call it as one epoch period. So this is the time till between which all the elements of the cache have been rewritten using the new key. So the two important parameters, one is the epoch period that I explained just now. And then we have remap rate. So we remap the lines of the cache using the next key, and this remapping is done is controlled by a parameter called remap rate. And remap rate of, for example, of 1% will mean that one line is remapped every 100 cache accesses. So naturally, high remap rate will mean that the epoch period is small. And if we do this remapping more frequently, then of course the system will be more secure. So next we see some attacks that the authors have come up with to attack these randomization based systems. So they have proposed two algorithms. One is group elimination method, and the second strategy is to exploit the replacement policy to remove the.
Siddharth,
Yes, sir.
yeah, don't start teaching. Okay. It's good to have, 1 point and then explain that point before you jump into all the ideas, right? Okay. So just follow that. And then I can see that there are so many text, the slides are full of text, no animations, nothing. What happened?
Sir,
Because
actually,
otherwise it becomes like a theory course.
yes, sir. The images are scattered here and there, but only few slides are there text.
Okay, move on.
Yeah. So this is the before the paper, this paper was proposed, the state of the art technique for finding the eviction set. So the problem statement is as follows: we have L lines, and we have to find W plus 1 conflicting lines among them. So W is the number of ways in the cache. So the strategy here is to hold out one line from the cache and then one line from this list, and then test the remaining L minus 1 lines. If the conflict occurs, then we remove the holdout line from the list, and this process is repeated till we are left with only W plus 1 lines. So here is a brief run of the algorithm. Let's say we have this 28 lines, and we know that, for example, we know that A, B, and X are the three conflicting the form eviction set in a two-way cache. So first we hold out this line. We know that the conflict won't happen. Then we are left with this much. And after 7 tests, this is what the algorithm state will look like. And since we are only decreasing our list size by 1 in every iteration, the number of accesses will be of the order of L square. Next, we see a group elimination method, which is faster than the single holdout method. So in this algorithm, the key change is that instead of holding out one line, we hold out a group of line. So we split the lines into G groups, and each time we hold out one group and test the remaining groups together. And if a conflict occurs, then we ignore the held out group because it is not necessary. And then this process is repeated till we have W plus 1 lines. So here we have divided these 28 lines into groups of 4, and first we hold out this group, and we can see that there will be a miss, and so we can discard this group, and after 7 tests we are left with this many lines. So because we are eliminating a group at a time, the complexity comes down to order L, and this is fast. So this is a brief comparison. Here we are eliminating one line at a time, and we are eliminating a group of lines at a time. And because this is quite fast, the time taken to attack a cache with Caesar will be lesser here. And for example, with remap rate of 1%, SHM will take 100 years for an attack to succeed. But in case of GEM, with a remap rate of 1%, it will take less than 1 second for the same size of cache. Then the second strategy that the paper has proposed is to exploit the replacement policy. So for example, if we know that the replacement policy is LRU, then we don't need to even do the GEM group elimination method, because we know that if we provide a thrashing kind of pattern, then there will be misses, and so we install the lines in a particular order. If we know that there is a eviction set inside this conflicting list, then we just access it again, And we know that for sure first A will miss because X has already replaced A, and then B will also miss, and then X will also miss. So with only 12 number of accesses, we can find out the eviction set if we know that the policy is LRU. Then since all the modern processors use some kind of reuse based policy, so they took a representative example of reference interval prediction, where they found that uh, just installing the lines won't work, so they have to install and upgrade the lines. Upgrade in the sense they have each line is associated with some reuse bits. So what they do is if they do multiple accesses, then the reuse bits are set to 0 for each line, and if all the reuse bits are 0, then it behaves like LRU. So since it behaves like LRU, then we can do just one thrashing pattern, and then again we will get these misses. So for RRIP, we can see that it only requires 3L number of accesses. Similarly, in the worst case, if we have random replacement policy, then we can just do like this. Let's say we already know X, we know a clash line X, and we want to find an eviction set with respect to X. So we just do X, and then we select a random line, and then again test X. And if the second X is a miss, then we can say that this random line is part of the same set. So we repeat this process, and on an average, if we assume that the probability of this random line falling into the same set is 1 by n, then we can say that on an average, if we do n accesses, then we can find one such element. So if we need w such elements, we roughly need 2 wn accesses on an average. So these are the fast attacks that can actually attack can be used to form eviction sets in Caesar before the remapping is completed, and hence the attack is successful. Before we go to the mitigation techniques, maybe we can take some short questions. Hello?
Yeah, looks like there are no questions, so you can move on.
Okay. Now that we have fast eviction set finding algorithms which can attack this random mapping, even the random mapping, so the paper comes up with some techniques which are still resilient to these fast attacks. To mitigate such fast attacks, they have used a concept of skewed associative caches. So traditional set associative caches looks like this. So for each set there are some number of ways, but in skewed associative cache, the ways are divided into partitions, and each partition is governed by its own hashing function. And for this reason, a set X can map to different set under different hashing function, and hence in different partitions it can map to different set. So this selection of partition is done randomly, so we don't know which side X will go, and depending on which side it goes, it uses the respective hashing function. So here there is some kind of non-determinism introduced into the system, and this results in some kind of robustness. Each line can reside in multiple possible sets, and because of this, there is some unpredictability. And because we don't know which side it will go, a group of lines which will go to the same place, that also is unpredictable. And that's why the eviction set formation is also difficult, because the elements of the eviction set, we also don't know on which side they will go. So, but there are also some limitations. Like we saw the hashing functions h1 and h2, they are static. So we have a lot of time, and we can reverse engineer those functions. And once we reverse engineer those functions, then we can find such examples where the same set, the same element maps to the same set on both the hash functions. So for example, if we consider the example of A, we can find such an A which maps to the same set as X on both the sides. It's of course more difficult than finding in this kind of setting, but it can be done since this H1 and H2 are static. So since this the problem arises because of this static hash functions, what we can do is that instead of having this h1 and h2 as static functions, we deploy Caesar instances on both sides, on both the partitions. So their idea is that they combine the idea of skewed associative cache with Caesar, and they divide the ways into multiple partitions like the skewed associative cache, and each side uses its own set of keys, and one line can get mapped to different set on either partition. So here in a cache which supports this skewed Caesar, the read is done same as the conventional type. So both the side get the address, and depending on whichever side there is a hit, they will return the data. And on miss, they have to randomly pick a partition, and victim is decided by the replacement policy of the partition. And for remapping, like we saw, we have to remap a line when the key changes. We have to read the line using the old key. We have to invalidate the original location, and then write the remap line into the new set. And writing here has the same definition that we described before. And the security, from the probability perspective, we can see that the probability that two elements map to the same set in Caesar S is 1 by S square will be proportional to 1 by S square, because we have to see that it has to map to the same set on both these sides. So there are S sets on both sides. So 1 by S is the probability that it will map to the same location on one side, and 1 by S square on both these sides. So we can see that there is an order of difference here, and S is quite large for large cache. That's why the security here is very high. And even with the group elimination attack, the authors have found that 1% remap rate will still provide 100 plus years of time for a successful attack. So here are the performance overhead. When the number of partitions increase, so S2 is the default implementation, S4 is where there are 4 partitions, S8 is where there are 8 partitions. So when the number of partitions increase, the performance, the slowdown is increasing, because each partition will get limited number of ways, and because of that the policy, the replacement policy is not able to learn properly, and that's why we see a drop in performance. Then we see the sensitivity to remap rate. Naturally, if we increase the remap rate, that means we have to remap the lines more frequently. That means reading the line, then again writing the line. That's why there will be more performance overhead. And for remap rate of 1%, which is quite secure for skewed Caesar, we see that the performance degradation is less than 1%. Then we see the sensitivity to LLC capacity. So if the LLC capacity is increasing, then the performance the relative performance drop is also increasing. This is because that because of the fact that the encryption and decryption latency of the block cipher is assumed to be 2 cycles that of the implementation they have chosen, and because of that when the cache size is high, the hit rate will also be high, and the decryption latency dominates this high hit rate, and that's why the slowdown is more in cases where the cache size is more. Coming to the overheads, the energy overhead primarily comes from the encryption decryption circuit, and because of the extra remapping overhead, and all of this comes to less than 1%. Coming to storage overheads, each block will need to store 1 bit each block will need to store 1 bit that depicts whether this line has been encrypted using the previous key or the current key, so that we know whether to remap it or not. So for this kind of status, we have to store 1 bit per cache line, and then we need 2 keys per partition. Each key is of 10 bytes, and then we need 1 set pointer to denote which cache line which set is our next up for remapping, and the number of accesses also we have to count, because we are doing remapping per 100 accesses or per 200 accesses. So like that, we also need to store the accesses. So this comes to 48 bytes per partition, and this is 1 bit per cache line. So this is quite small. And of course, increasing the number of partitions will increase the second two overheads, because each of them will require their own keys and set pointers and access counters. And although it will be more robust if we increase the number of partitions. So that is all. If there are any questions.
It seems there are no questions. Yeah, overall, there's so much information, but in terms of presentation, it was below par. You should have actually put precise information, maybe in the form of bit of figures, animations, right? Otherwise, it was giving a feeling that you're teaching like a prof, right? So these are the things, these are the issues, and then you're kind of explaining it one by one, like providing notes, right? Yeah, that's my feedback. There are no questions, seriously?
Hi, Siddharth.
Yeah.
There is a question. See, when you increase the LLC size, right? Probably the penalty of increased latency should maybe means mask the performance overhead, right?
Sorry, penalty of increased size.
Increased latencies. So how have this size been increased? Have you kept the associativity same or you have increased the associativity? Because if by
No.
doubling the associativity, probably the latency increase in latency penalty will be still more.
Yeah, so they have kept the number of ways as 16 in all the caches, and this
Okay.
experiments in the baseline is also performed on the bigger cache. So it's like the baseline cache will also have, for example, here 32 MB, and the Caesar and Caesar S will also have 32 MB. So this is normalized performance.
No, but I still couldn't get. Means my question was, if we increase the size of cache, can we mask the overhead penalty due to all this encryption, decryption stuffs? Because the performance penalty is basically due to decryption, right?
Yeah, of course. See, like this 32 MB cache, compared to this 8 MB, this will of course be much faster. But relative to the baseline 32 MB, it is slower, and the gap is much more than the gap between the baseline 8 MB and the Caesar 8 MB. This will
Okay.
be the 32 MB will be faster than this 8 MB implementation, but the slowdown is more with respect to the corresponding baseline.
Okay. Okay. Sorry.
Okay, then I guess Devasis, you can stop the recording. Devasis, are you there?
Yes, sir. I've stopped the recording.
Okay. Okay.